Another way to think about arc length for polar coordinates is just turn it into xy data, like just decide a small increment for theta and generate r comma theta data, then turn that into xy data, and then add up the various small increments of arc length. So we'll try that. Let's try it in a spreadsheet. If we're using the other view of arc length, we'll need to know arc prime. If we know a formula for r, we could just take the ordinary derivative, but if not, or if all we have is polar data without a formula, we can approximate r prime using basically, well, how much did r change and how much did theta change, and dividing the two is like dy over dx. So that's called a forward difference or backward difference quotient, depending on whether you look at this row and the previous row, that would be backward, this row and the next row, that would be forward, or the next row and the previous row, that would be central. So we'll give that a try in our spreadsheet. We'll also try a new polar function that we haven't played with before. This is how you do an ellipse, or one way of doing an ellipse in polar coordinates. This E-looking thing is the Greek letter epsilon, and it's used for the eccentricity. So if the eccentricity is 0, you just get 1 over 1 minus 0, which is 1 over 1, which is the unit circle. So that's it's not eccentric at all. And if you force the eccentricity to 1, you're going to end up with a divide by 0 every now and then. So your ellipse is going to go off to infinity in one direction, which might actually be a parabola, which is an interesting way to think about things. How would we take r prime here? Well, we could use what? The quotient rule, or we could say it's the denominator to the -1 power and then use the power rule and chain rule. Or we could go practice our spreadsheet skills and do forward difference and backward difference quotients. So let's go do that all in Excel. All right, here I've got a formula that uses an eccentricity that has its own cell, so I can change that easily. And here's the result I'm getting. To get this plot, of course, I had to compute the radius as a function of theta, and then over here I had to compute x and y, so I can plot it in Excel. Does this look like a highly eccentric ellipse, something that's really squashed compared to a circle? It doesn't look all that squashed here, but notice that the y-axis is like plus or minus 2, but the x-axis is from 1 to -6. So if we actually tried to make this equal directions up, down, and left, right, and aspect ratio of 1, it would end up being more spread out. Like what's on the screen here is that much. I would need to make -2 to 2 be that much in the left-right coordinates, so I'd actually need to do that somewhat. Let's play with the eccentricity a bit. What if I set the eccentricity to 0 and try to get back to a 1-to-1 aspect ratio here? So that's reasonably a circle. What if I set the eccentricity to 0.5? Again, the Excel is changing the aspect ratio on us, so it's kind of a pain. What if I set it to 0.99? So now the x-axis goes 20 to -120, but the y-axis is still only like plus or minus 8. So we would really have to stretch this out to get a 1-to-1 aspect ratio. It's also interesting that the data is more spaced out over here than it is over there. What if we try 0.999? Then it's really very spaced out over here. Let's try another 9 there. So spaced out, we're kind of missing the curvature. And what if we try another 0.9 there? Wow, that we're taking basically one data point way out there. We can try dialing it back a little bit and see kind of how we got there. So anyway, lots of fun with eccentricity. Let's go and calculate arc length. So we need to calculate r prime, and then the length of this little segment and the total length so far. So what is the rate of change of the radius from this row to the next row? That would be difference of the r values divided by difference of the theta values. So here I'm doing a forward difference quotient because I'm looking from this row to the next row. I'll fill that down. And then the length of this segment, what's that formula from that integral? It was square root of r squared plus r prime squared times d theta, like that. And we'll fill that down. And then the total length so far, we'll start with 0, and then we'll say my new value is my old value plus the length of the most recent segment. And we get an answer. If you ever see all these $signs in Excel, that just means the cell was too wide to show all the decimals it wanted to do. So just grab the divider bar between the columns and move it to give it a little more space. This last answer here is using a blank row, so that's garbage. We want to delete that. So is 14 a reasonable answer here? Well, I mean, we can look at the graph and say, well, it's going from like positive a half to negative 5, so I'm not thinking the arc length would be 1,000,000, or the arc length should be at least 0.5 minus negative 5. So it seems like we're in the right range. But here's a really useful trick in all of math and science, not to overstate it. Try it on a simpler case where you know what the answer should be and see what answer you get and see if it's the answer that you should get. The simpler case would be an eccentricity of 0, where we would just have a perfect circle and it goes through 1, 1, negative 1, negative 1. So that's the unit circle. So what should the arc length of that be? Let's go take a look down here. It's apparently 2 pi, or at least pretty close to 2 pi. Given that I'm only taking a non-zero step in delta, delta theta, I think we're getting a pretty reasonable answer there. So at least it works for that simpler case. So remember we had two views of arc length that gave us the same formula involving square root of r squared plus r prime squared times delta theta. The third view we had was, hey, let's just turn it into xy data, which we're already doing here to graph the polar curve. So then we can say, what's the length of this segment? I've got these grayed out because I wasn't using them before, but now I am using them, so I'll ungray them out. What's the length of the segment from here to there? That would be difference of the x's, so new x minus old x squared plus new y minus old y squared. And notice that that is pretty close to this, but not quite the same. And we'll fill that down. And our total length so far, again, we'll start with 0, and then previous total length so far plus that. And we'll fill that down. And let's go see which one was more precise. Remember, this is for a perfect unit circle now. So it looks like all that calculus effort got us a more precise answer than just drawing the little distances from one xy point to another xy point. That's because that calculus formula is basically presuming we're moving in a small arc of a circle rather than moving in a straight line from point to point. Here it's not a big difference, of course, but if we were taking larger theta steps to take less time in all the computation, then it would make a larger difference. We can also go try some other eccentricity and see if we get close to the same answer. So yeah, pretty close, but that's good to compare two different ways of doing things, and when they're pretty close, then we can have reasonably high confidence that that we're doing the right thing both times.